Test. All right, good evening. Let's get started. In the previous lecture, we started a new topic called vector field. All right, so the vector field, we demonstrated basically what a vector field looks like for some very simple vector function. This is the example we have demonstrated. Right, so if you have a vector function like this, it presents a radial vector field out of the origin. And if your vector function like this, then you literally have a spinning vector field. Okay, and the far away from the origin, the bigger magnitude of the vectors are. Okay, so that's essentially the idea of a vector fields, how you build a vector fields, and they're all based on the vector function. So today, let's look at what we can do within a vector field. And the first thing we'll look at is so-called vector line integral. Okay, so I'll start with a simple example, and then we'll lead into a general expression of a vector line integral. Okay, in dynamics or in physics, okay, so we have learned this simple idea of a work. So if you apply a force horizontally, and then the object moves a distance of d, and assuming that your force is applied as a constant value, then you know that the work done by the force is F times the distance, right, or displacement. All right. Now, if your force is actually applied with an angle, okay, to the horizontal direction, and you do exactly the same thing. Okay, push it for a distance of d without changing the force, the magnitude and direction, then we know, okay, so work again equal to the force times the distance. Okay, but this time, right, this is basically you have to get the, if force is considered a vector, then you have to get the component of the vector in the horizontal direction, which is basically direction along the displacement, and then times the distance. And distance could also be a vector, right? So let's use this absolute value vector here. So this is in terms of vector notation. And we also learned that this is basically your F dot D. Okay, so if you use a dot product, that's F dot D. Okay. In our first lecture, we also have mentioned every vector has two components. And the vector has a component of a direction and also a component of magnitude. So F dot D is equivalent to F dot D hat, and then multiplied by the magnitude of the D at here, right? Okay, so this is the work done by the force, okay? A single force without changing the magnitude and direction. Then you end up with the formula F dot D hat and times this absolute value of D. Okay. Absolute value of D refer to the displacement, the travel by the object from here to here, right? Okay. So now you can establish sort of in your head, you know, total work, okay, in general, right? If a force is constant, and then is constant during the time of travel, then the formula basically F dot D hat, and then times the absolute value of the D. Okay. So now let's extend this to more general scenario. So now let's consider this situation. So let's say I have a path, okay, in the 3D space. And we call this curve is represented by a parametric equation R of t. So this is a curve represented by R of t. And you place this curve, or immerse this curve within a vector field. So, okay, so basically you pick any point within this 3D field, right, including the points on the curve, right? So imagine that there's some sort of vector fields exist in the 3D space. And this curve is being placed within that vector field. So at a different location, you might have a different vector representing the vector fields. So at this location pointing that way with this magnitude, at the different location pointing to a different direction with a different magnitude. Okay, so it's much more generic, complicated. So then the question here is, here's a question that we're going to look for is, so what will be the total work done, okay, by the vector field? But in this case, okay, so this vector field F, so we can call it force field. Okay, so it's like this F is basically it's all about the force. So what would be the total work done by the vector field, okay, over the curve C? So you can imagine, you can sort of visualize if I have a mass starting from this location, then it's like at every location along the curve C, there's a force pushing it, right? It's just pushing it with different magnitude and also at the different, maybe at a different angle. But that object will be pushed from one end to the other end. So the question is, what will be the total work done by that vector field or force field over this curve C? So that's what we want to find out. Okay. So here's what we can do. You can pick anywhere along this curve C. Okay. So let's say you pick somewhere over here. Okay. And then you could pick a very, very small segment of curve, okay, based on the curve C. So let's say right at here, this location, right? So I'm going to define a new vector. So from here to here, so let's say I'm going to define a new, let's get rid of this force here. Okay, let's just put it somewhere over here. Okay. So let's say from here to here, I'm going to define a vector. Okay. And this vector, I draw it a little bit away from the curve, but in reality, if it's very small, so it's so close to the curve C. Okay. And this vector here, I'm going to call it as a ds. So ds at here is a vector. It's a so-called, basically, it's a differential displacement vector. It's a differential displacement vector. So displacement is a vector, right? You know, you go in this direction, displacement, okay, go how much you go and what direction you're going, and that's displacement vector. This time we're defining it as a differential displacement vector. So that ds technically, okay, every vector has two components, direction and what, the magnitude, right? So this ds city here has also two components, direction. So direction is the tangent vector along this curve C. And magnitude, I'll just use the ds, the amount of arc length or segment of a curve length, right, as a direction, as a magnitude for this ds vector. Okay. So this is the definition of ds as a t hat ds. Okay, yeah. So if this is a very small, of course, it's a differential. So then within that part of this displacement, I can consider the force field is not changing. It's a constant, just like from here to here is a constant force field, vector field. So then I can calculate the small amount of work, okay, done over that ds. According to the formula we have derived, right? How much work can be done when you maintain a constant force vector and then push it over a certain amount of a displacement d is f dot d hat multiplied by its magnitude, right? So then over here, the amount of work done is the force, okay, at that location, and then dot t hat ds, which is basically this ds vector, is how much work can be done over this small differential displacement. Okay. Or you can write it as f dot ds, okay, it's the same meaning. So that's how much differential work is done. But you really want is a total work, right? So total work, then the total work is just integral of the dw. And you're integrating over the curve C, right? You're adding up all the small work and you get a total work. So basically we're integrating f dot t hat and ds, or equivalent is f dot ds vector. And this is much more applicable as you're going to see next, right? So now you see the question that we wanted to answer give us an integral operation. So this operation here is what we call the vector line integral. So this is called vector line integral. Because apparently you can look at the integral here, what does it involve? It involves vectors. And you're integrating these vectors over the curve C. Okay, so that's why it's called vector line integral. And in the previous lecture, maybe I can't remember, before the midterm or right after midterm, we learned a subject called the scalar line integral, right? So this is the counterpart, it's called a vector line integral. So the derivation in here, we considered F, which is a vector field, as more or less of a force vector field. But in reality, so in general, I don't have to consider this as a force. I don't have to think of this as total work done. In general, I could just consider as, let's see, in general, given a vector field V and a curve C, okay, then you can just simply write down the vector line integral like that. Okay. So mathematically, right, for any given vector field and any curve C within that vector field, you can always just write down the general vector line integral formula like this. All good? Okay. And the other thing also I want you to focus on is just look at this term at here, right? Look at this integral term v dot t hat. Okay. If you can relate to one of the concepts I think we repeatedly emphasized a little bit prior to this lecture is when you use a vector dot a unit vector, what does that give you? Right, when you use a vector v and then you dot a unit vector t hat. So v dot t hat, if you recall that gives you the length of the projection, right? So mathematically, what this integral is doing in here. Okay. So basically, this one is the length of projection of v in t hat direction. Okay. Right? This is just at one moment, if you have a curve C, and if this is the t hat at this location, and if this is the v in this location, then what you're doing is you are projecting the v in that direction t hat, and you get one projection, length of projection. And then consider really at each location, right? At each location, you have a t hat. and you have a V. So at each location, you're doing this. And then integration over curve C, basically you're adding up, right, all of the lengths of the projection of the V in t-hat direction over the curve C. Right? That's called integral, right? Summing up all of this. That's basically what vector line integral is doing in mathematics. Okay. Now, if, right, let's make it a little bit more concrete. If V actually represent, let's for example, a flow of water, right, a certain kind of a flow of water in the 3D space, then what you're adding up at here is, right, so basically what you're adding up, you can call it, you're adding up the total circulation, okay, of this water velocity V along the curve C. Okay? Right? That's basically what this vector line integral is doing. You're adding up the total circulation, okay, along this curve C. A circulation of what? Circulation of this V vector field V. You know, could be water, could be maybe a speed of air, okay, or could be, in that case, as a force vector field. Okay? So you're adding up the total circulation of this. This is actually a very useful tool. In the previous lecture, I showed you a graph of airfoil inside, for example, a graph airfoil inside, right, a wind tunnel. Okay, so if this is an airfoil, very rough drawing here, so you could basically consider there are, you know, certain kind of a vector field, okay, or a speed of the air, okay, circulating around this airfoil. Then you can technically calculate the total circulation of this air circulation over this airfoil. So I used a circle here, basically means the C here is a closed curve, right, instead of an open curve. So you can get a line integral over this. So let's call this is gamma. Okay, you can call this is gamma quantity. Okay. And then there's a very famous theorem called the Kuta-Joukowski theorem. So that theorem basically you multiply the fluid density rho, and then multiply by u. U is the speed of the body relative to air speed, and then multiply by this result of the vector line integral. Okay, so then you got the L, and L is basically called the lift force, okay, over this airfoil. L is the lift force. Rho at here is fluid density. The U there, capital U, is the speed of the body, okay, relative to air speed. All right. So that's a simple application of this vector line integral. So the question for the next maybe 10 to 25 minutes is, how can we compute this vector line integral, okay, based on some given conditions? Okay. So let's take a look at some examples, how we can do the calculation. Given a vector field, YZ, XZ, and XY. So here is a vector field and a curve C. T square, T cube. Okay. we want to calculate the vector line integral over the curve C. Okay. Okay. Now, before we proceed, I probably should derive a little bit about the formula, but that's okay. We can use the example to derive the formula here, right? So let's look at this formula. So the formula requires the vector field F. We already have it over here. And it also involves the t hat. So I think you need to bear in mind what t hat is. T hat is the unit tangent vector, right, for the curve C. Okay, that's t hat. Okay. And this, the other one is a quantity ds, right, ds. And ds, as you can see in the illustration and here, where is it? Over here, right? ds is basically the small differential displacement or arc length along the curve C, right? So ds essentially is the magnitude of the ds vector. Or in other words, it's a very small arc length or displacement along this curve C. Okay, so these two quantities meaning are listed over here. So ds is the differential arc length okay, on curve C. All right, so let's put together everything that we have learned previously, okay, into this formula. Okay. There's nothing we haven't learned yet. Okay, so first of all, let's deal with the ds. ds is the differential arc length. So if you look at one of the lecture notes, and I can't remember which lecture notes, when you are given the parametric equation for certain curve C, then its differential arc length is dr over dt dot dr over dt and then times dt. Right, that's the formula that we derived when we learned the scalar vector line integral. And R right here is the parametric equation for the curve C. Okay. Inside, you have a dot product of the derivative R over dt of itself. And this is equivalent to write it as dr over dt, absolute value, dt. Your dot product is a scalar quantity. Okay, so you should end up with a scalar quantity. This is your ds. And then the next quantity is t hat, unit tangent vector. So t hat, we have also learned, if you have the parametric equation for certain arc or certain curve C, then its tangent vector is dr over dt. And then you normalize the tangent vector, so you will get the unit tangent vector. Okay, so that's t hat. Good. So now I'm putting this together. So let's say what's t hat multiplied by ds then, right? T hat multiplied by ds. You can clearly see the denominator here is the same as dr over dt over here. So the t hat times the ds, okay? So maybe I'll just write down the original formula. F dot t hat ds is equal to F dot t hat, let's rewrite the t hat. And then times ds. Okay, so you can cancel these two terms. And then you get right, dr over dt and dt. I typically will stop here, will leave it as it. Sometimes you can see in my lecture notes or in textbook, they also cancel the dt. Okay. I don't think you need to cancel the dt because if you cancel dt, that's fine. But when you calculate dr vector, your dt will actually show up again, essentially. Okay, yeah. So you can leave it as you don't need to cancel this dt. You could just leave it as it is because you're integrating with a dt, right? With a dominant variable. Yeah. And with the integral here, you need a dt anyway. And you also calculate derivative dr over dt anyway, right? Okay. So that's the shortened, the derived version of this vector line integral. So up to here, you have the r, so you can definitely calculate the derivative r over dt. So the next question is, how do we deal with f vector, right? How do we deal with f? So this is where I'm going to use this example to demonstrate the actual calculation, okay? Yeah. So for this example, your r equal to t squared t cubed. Then dr over dt is 1, 2t, 3t squared. Okay, so that's simple. So then f, okay, f is a vector. Now let's go back to the f. Y, z, x, z, x, y. So let's rewrite it over here. Okay. So first of all, you're not going to mix x, y, z together with a t in one single integral, right? Then you can't do anything at all with this mixture. And the integral here, you have in terms of a t. So you're integrating over the t, okay? And also go over the curve c. So the range of the t will be based on this, actually the curve c at here. So then what do we do then? The f it's a vector field in principle, is a vector field exists anywhere in 3D space. However, you're integrating only over curve c. So you're not really looking at anywhere. You're only looking at what? Only looking at the points over the curve c. So all you need to do is you replace the y with y of t, and this is your y of t here, this is your x of t, and this is your z of t. You replace the x, y, z with the parametric equation from the curve c. So y is y of t, z is z of t, and x is x of t, like that. So in this case, you get y is t squared, z is t cubed, x is t cubed, x is t squared, right? So you're replacing x, y, z with the x of t, y of t, z of t components of the parametric equation. Okay. So this way, you can simplify this a little bit. You get t to the power 5, t to the power 4, and then t to the power 3. Interestingly, it's just reverse the order here, right? Okay. Now, my f, my dr over dt, everything is in terms of t. Okay, so everything in terms of t, then I can actually carry out the integral. Last piece of information is then what will be the range of the t or the integral limit for the t, right? So the question typically should give it to you. I don't think I give it to you yet. So t go from 0 to, let's see, in this question to 2. So let's force the t go from 0 to 2 as the range for the curve c. So then last step, you plugging everything into this vector line integral. Okay, t go from 0 to 2. You are doing dot product of f dot this dr over dt, and then dt. Okay. So dot product, I think everybody should be able to calculate. So t to the power 5 plus 2t to the power 5 plus 3t to the power 5 dt. So calculate everything, so you should get 64. Okay, so that's the generic approach of how you can compute a vector line integral. So if we revisited this question in here, let's see what's involved, right? When you're required to calculate a vector line integral, so ultimately you don't really have to use this formula. You're using this formula here. So you're required to calculate derivative of the vector function representing the curve C, and you have to substitute the parametric equation of the curve C into the vector function f. So then you can eliminate all the x, y, z, and you end up with a pure function of t, or vector function of t. Then you do dot product, the range or the limit for the t. So usually will be given by the question. If a question is not given, maybe the question given is, okay, from this point to the other points. So you can use the coordinates of the starting point and end points to get actually the value of this t, right? Which I think one of the assignments was like that. So the rest of the work is basically just regular integral, okay? Okay, now I want to show you an alternative appearance of the formula. Alternative means there's nothing different, it just looks different, right? So here is the vector line integral, dr over dt, dt. Okay. Now, let's say, consider a vector function f is given by 3 components, m and p. So I'm just basically writing the 3 components of f using 3 functions, m and p. Now, each one of the function, if you really want to write it out, they can be a function of x, y, z, right, for each one of the components. And then you also have the r, it's probably also given as x of t, y of t, z of t. So those 2 are given. And then if I start to substitute these general symbols into this formula for the vector line integral, let's see what do we end up with. And first of all, for this formula, as you can see, you can certainly cancel this, okay, that's fine. So if you cancel this, then it becomes f dot dr, okay, differential r. Now I'm gonna substitute f and r into this formula, okay. Then I would get, so f dot dr. Okay. So f is m n p dot, and r is x of t. Sorry, dr, right? You got a dr at here, so you got dx of t, dy of t, dz of t. Okay, that's dr. Now m and p, of course, before you carry out the next step, as usual, what do? You replace all the x, y, z with x of t, y of t, z of t, of course. That has to be done, right, before you proceed. But after you've done that, for this dot product, you basically end up with m dot dx of t plus n times dy, and then p times dz. Okay. So this is what I call an alternative appearance of this vector line integral. You're literally basically separating this f using its component m and p, and then right, each one of the derivative dx, dy, dz is actually derivative of the vector parametric equation for the curve C. Okay, so this can work, and if you use this formula, it can also work. So let me give you an example here. Okay, but I find oftentimes, based on my experience, I find a lot of students actually confused with this formula. So if you're not comfortable with this formula, I wouldn't suggest that you use this formula. Okay, but I want to demonstrate just one example here. So let's say I have a vector field F, and then t go from 0 to 2. Okay, and also has a vector function parametric equation for the curve t square. Okay. So when you say t square, it's basically actually y equal to x squared. Right? So when you replace x with t, then y is t squared. Right? That's basically a parabola or a curve in the 2D sense. Right? Okay. And the other thing is, this is basically your m component. This is your n component. Okay. Now you can absolutely try the approach that we have done, right, in the first example there, how you can calculate. But let me demonstrate how this formula can also be done. Right. So m, what you need to do is you need to replace. Okay, this is a 2D, so when I have a z component, you need to replace the xy with the x of t and y of t. Okay, so this is your x of t here, this is your y of t. M is only negative y, so basically you replace the y with t squared, so you get a negative t squared. And n at here, same thing, n is just the x, so you replace the x with t, so that's t over there. Okay. And now the dx, so this component dx at here, okay, is actually dx of t, or dx is t, right? So that's actually nothing needs to be done. So dx basically is dt because x of t is t. Now dy, okay, you replace the y with t squared. So it's a differential t squared. So this one you need to do something. So that's 2t times dt. 2d times dt. I often find a lot of people still having trouble with difference between differential and a derivative. There's a little bit different. So you see, if you calculate, this is called derivative, right? This is differential. Right? The derivative gives 2t, and differential give you 2t dt. That's the difference. Right? That's why you get 2t dt, and derivative just a 2t. Okay. So now you got each one of the components for the formula, so we don't need to worry about the z because it's a 2D, and you substitute everything into the expression at here. So you end up with, okay, you're integrating from 0 to 2, and get a negative t squared, which is m, at dt, and then n of t is t, and multiply by 2t dt. That's your dy. Okay. So, and that's it, right? You put everything together, you calculate the integral, you'll get a over 3. So this is the idea, right, of the other, how you can use the alternative formula, and this alternative formula here. So whichever you feel comfortable when you practice, right, you can choose the right formula, but doesn't matter which one you choose, you should have the same results. Okay. But I find some students not quite comfortable with this formula. So if that's the case, then I would recommend that you use this formula here. Okay. Yeah. All right. So this is basically the idea of a vector line integral. Right? You integrate certain vector field, okay, over a vector, over a parametric equation curve, over a curve C represented by a parametric equation R of t. Okay. So before we go ahead, let me show you one more example. And this example is more of a demonstrating the understanding of your concept at here, okay, rather than calculation. Right. So here's a vector field f of x equal to xy, and then curve C is the circle, okay, x squared plus squared equal to a squared. Okay. You are required to calculate, okay, the vector line integral over this curve C. Okay. So if you have to draw a demonstration in here, so this is your curve C, it says it going counterclockwise. And then you also have the vector field xy. So if you have to sketch the vector field, right, you don't need to sketch a vector field other than the point on the curve C. You don't really care the vector field at this location because it's not on the curve C. So let's see if I pick a point on the curve C. Then this point has a coordinate xy. And the vector field is xy. So basically your vector at this location, right, in the vector field is a vector from here to here, right? So that's xy. Okay. It's a radial vector essentially attached to that location. Okay, so how would you compute this vector line integral? A typical approach is you need to obtain a parametric equation first for the vector for the curve C. So if it's a circle, so a cosine t, a sine t, and then t go from 0 to 2 pi. Okay. And then next you do, right, you can substitute x of t, y of t into the vector function. And then you do the dot product, and you do the derivative, and you calculate the rest of things. Okay, that's a typical approach. Okay. However, for this question, I want you to look at the original formula of a vector function, a vector line integral. This is the original one. Okay, so look at this original one here. What's the original? F dot t hat and ds. So remember what t hat is. What's the t hat? What is the definition t hat? Unit tangent vector. Unit tangent vector to the curve C. Okay, so then if at this point, can you sketch the unit tangent vector? What will be the unit tangent vector? It goes counterclockwise, right? It's tangent. So I guess you would draw a tangent vector, okay, at that location. Okay, so now you're calculating the dot product of this vector with the t hat. So f dot t hat. So what is the geometric relationship between the t hat and that vector xy, which is a vector field? Perpendicular, exactly, right? If they're perpendicular, then f dot t hat at that location must be 0. Now, if I pick a different location, I think I'll get exactly the same relationship, right? So as you're going along the whole curve C, doesn't matter where, the f dot t hat is always 0. So the whole vector line integral should end up with 0. Right, that's a quick way to solve this question rather than doing step by step, right? By all the substitution, derivatives, and integrals, and you end up with a 0 anyway. Good. So if you look at the computation involved in the vector line integral, it's not that bad. Right? You just have to follow a few steps and carefully carry out the integrals. Okay, just have to plug into the right piece of the puzzle there. Now, still have a few minutes, so I want to touch upon another important topics, and we'll look at it as a little more detail in the next lecture, of course, is conservative fields. Okay. So we're slowly getting into making use of the prior knowledge. Okay, and conservative field is one of the new topic. Okay, we're going to look at it. So what is a conservative field? Okay, first of all, so I would say it is a special kind of field. So it's not a generic vector field. It's a special kind of vector field. Of course, it's special, right? So here's a statement. So the statement is a gradient vector field. Okay, what's a gradient vector field? Is if you calculate a gradient vector based on a scalar function f, okay, so depending on whether you're talking about it's a 2D or 3D, okay, but as long as you calculate the gradient of a vector function, a gradient of a scalar function, right, and you will end up with a vector field or vector function f at here. So we call this is typically we call it gradient vector, right? But if you plug in different numbers, x, y, z, or x, y into this vector, then you got a whole spectrum of vector field. So this is called a gradient vector field. And this gradient vector field is a conservative field. Okay. As we're going to see later, any conservative field, okay, basically will be able to be described by del f. So if you look at what you're looking at as a conservative field, if somebody says, okay, this is a conservative field, then in the next we're going to learn is we're going to show you, as long as you know that's a conservative field, then you will be able to find a scalar function f, small f, whose gradient operation will actually give you that conservative field. Okay, that's a connection at here. Okay, so I want to write it down as a statement for now, and we'll come back to this statement. We'll connect the dots between a vector, gradient vector field and a conservative field. Now, let me give you a couple examples of a conservative field, and then you know it's not really anything, just a pure mathematics. Okay. Number one is the gravitational field. A gravitational field, G. So we all know, if you stay on the surface of Earth, you have a gravitational constant, and if you go further up, right, into the space, and the G will get smaller. Okay, so that basically is a gravitational field. First of all, okay, we have a so-called V function can be defined as a scalar function, can be defined as negative Gm over R. Okay, so this is a scalar function. G is the gravitational constant, M is the mass of the Earth, and R is the distance from the center of Earth to wherever the interest point is. Okay, so this function at here, okay, is called gravitational potential function. So gravitational potential function. Okay, and then your gravitational field G is basically you apply the del or the gradient operation in front of this function, scalar function V. So del V give you this gravitational field G, which turned out to be just a capital G, capital M, R squared times R hat. R hat is the unit vector. Okay. So that's how you get the gravitational field G. As you can clearly see, right, how this gravitational G is obtained is based on the gradient operation of this scalar function V, which is called gravitational potential function. Okay. And gravitational field is a conservative field, as we all know. Conservative field basically means, energy is conserved, right? If you do work, as we're going to point out later, it doesn't depend on the trajectory. It doesn't depend on the route. Okay, that's conservative field. Okay. Another example of conservative field is electric field. So electric field, we're talking about, let's see, electric from a point charge. So if you have a charge or a particle just Q, okay, in the 3D space, right, this is Q, then there exists a electric field, right, due to this charge. So as you learned, probably you learned this in your 178, I believe. Okay. First, you can obtain a so-called electric potential. So this scalar function here is called electric potential. Okay. So we call this as a phi E. Obviously, this is a scalar function. Then the electric field due to this point charge will be simply calculating this gradient of this scalar function del E, del phi E, which you end up with just Q over 4 pi epsilon r squared and then r cubed. Okay. An electric field is another example of a so-called conservative field. And you can clearly, because it is a result of a potential function's gradient operation. Okay. So we're going to answer a couple questions in the next lecture, a couple lectures is, okay, so how do I decide a vector field is a conservative or not? If I know it's conservative, then how would I be able to find a scalar function so that its gradient is actually give me this conservative field? Okay. So we'll do a few things within conservative field too. Okay. All right, so any questions, feel free to come over here and we'll see you on Wednesday. So somebody asked about the formula for the final exam. I talked to the other instructor. I think we will post the formula sheets on Canvas. Okay. So of course, not everything has been covered yet. And again, I want to emphasize the importance of the last 2 weeks, 2.5 weeks technically. There are many things, highlights that that's actually part of this course. Okay. So you can use the formula sheet as a reference. Again, my suggestion is always, if you have a formula sheet, you have to understand how to use the formula, right? That's the most important.